Okay, well look, first of all, thanks for turning up. I appreciate that it's kind of early in the morning. And I'm going to make a gentle start to your day, because I'm just going to tell a kind of funny story, just based on some of my observations about APIs. I'm the maintainer of the Linux manual pages now for about 15 years. This is the manual pages that document the system calls, library functions. There's about 1,000 pages there. And I happened to write a book also on the Linux programming interface. So I spent quite a bit of time looking at interfaces on Linux over the years. And why am I standing here? It's because I'd like us to see us do APIs better. The problem about misdesigned APIs is they're usually unfixable, because if we try and fix an API that people are already using, probably we break that API for some other people who are already using the API and depending on the brokenness. And this means that when we have an API that is broken, its design is broken, it's usually set in stone, and a lot of user space programmers live with this misdesign for decades, and decades is really the time scale that we're talking about. And so we really want to get APIs right the first time, or at least better the first time. So what I'm going to do is just tell a story about a certain system call that was added to Linux, about 22 years ago now. And it was added with one new feature back then. By now this system call has many, many features, but back then it had one new feature. And I've sort of chosen this because it's quite a good example, and it seems simple at the start, and then when you drill down, it's surprisingly complex. And I'm not trying to say that the person who implemented this API did something wrong, but just really to show that even when something is quite simple, it can turn out to be quite complex. And I want to consider some of the ways we might do API design better in the future. And just by the by, there is a program there sitting on my website which you can use to observe these various surprising behaviors of this API. So this is the series of events. Okay, a lot of surprises along the way. Okay, so almost since the beginning of Unix, there's been a signal called SIGCHILD. It's the signal that's sent from that's sent to a parent process when a child process terminates. It wasn't there right at the beginning on Unix, but it appeared very, very early in the life of Unix. One day on Linux, someone decided it'd be useful to have the converse thing, and there was an email message sent to Linus on the list saying, look, I'd like to add this feature. A new system call called prctl, where you could set something called the parent death signal. The idea would be that when the parent process terminated, the child would get a signal. Okay. There was no explanation of why that feature was needed. This is a consistent pattern over the years. I just want it. Okay, it was a pattern back then as well. So, to begin with, I don't know if the author of that kernel patch contacted the manual pages maintainer of the time, who was not me, because I've only been doing it for 15 years. And there was no public mailing list back then, so there's no historical record. But anyway, a wee while later, Andries Proever, who was the manual pages maintainer at the time, added some documentation describing this new feature, this new system call and this new feature. The PR set pdeath sig, you say what signal you want the kernel to send you when your parent terminates. This is the signal that the current process will get when its parent dies. If you're a kernel developer, you know what current process is. If you're not, if you're a user space programmer, current process is kind of a meaningless term. They meant calling process. Okay, kernel developers sometimes need to get out a bit more. Okay, so now we've got this feature, the converse of SIGCHILD. You make this prctl call, you say pr set pdf sig, say what signal the child would like to get when the parent goes away, and seems really simple. And what could go wrong? Well, first of all, we had some missing pieces. So we've got the ability to set this attribute for a process, but then we might want to ask the question is, what is the current setting of this attribute? So then a wee while later, someone added a pr get pdf option to the system call. Again, it seems really simple. You know, how could we get that wrong? Well, we didn't exactly get it wrong, but we started a small mess. Because 6 months later, this mail turned up on the mailing lists. Look, 6 months ago, I added this new feature to the kernel, to the pr get pdf signal option, but I see someone else has added something called pr get dumpable, which was another option that was added to the system call. But these two getters return the information in different ways. One of them returns it as the function result, the other one returns it as via an argument. There's no reason for this inconsistency. Okay. Probably the way that pr get pdf signal did things was probably slightly better, in fact, because maybe the value that's being returned is not necessarily an integer, it might be pointed to some other kind of buffer. So returning via a pointer rather than as a function result is probably a better idea. Nevertheless, we ended up being consistently inconsistent. So now, by now in the current Linux kernel, there are a number of getter options for this prctl system call. 13 of them do it one way, 9 of them do it the other. Okay. Now, whenever a new feature is added to the interface, the question for me is always to wonder, well, how does that feature interact with other features that are in the interface? And I often find these areas are sort of rich veins for finding surprises. You know, process creation, execution of new programs, delivery of signals, threads. Threads is a really good one. And process termination. And there are other places for finding surprises too, but you know, these are often good places to start. So let's look for some surprises. Exec.ve. Exec.ve is the system call that a process uses to say, I want to execute a new program, replace the program I'm currently running with a new program. Now, in the original manual page entry for this pr set pdf sig feature, this was all the documentation there was, basically, and there was a sentence there, this value is cleared on fork. When I see a sentence like that, I immediately want to say to myself, because I always think about fork and exec, well, what about exec? There was nothing there in the manual page. Unfortunately, I didn't notice that absence until about 2014, I think it was, and then when I worked out what the answer was, I put in this text. The value is preserved on exec.ve. That's fine. Perhaps, though, if someone had documented that back in 1997, they might have realized, or maybe people would have thought about earlier, a possible security vulnerability. And so I want to go to signals for a moment. Now, one process can send a signal to another process. This is text from the kill manual page. The general rule about sending signals to another process is either you have to be privileged, in which case you can send signals to anyone, or there needs to be a credential match. In other words, you can only send signals to processes that belong to you. One process can only send a signal to another process if they have matching credentials. The question is, can or could we have taken advantage of this in conjunction with pr set pdf signal to send signals to processes that normally we couldn't send signals to? Now, being able to signal processes that normally we wouldn't be allowed to send signals to, that's the sort of thing that could be interesting for an attacker. So here's a picture first of all. This is what pr set pdf sig does. We have a program that calls fork. Okay, this program is presumably being run by an unprivileged user, let's say UID 1000. So if I've got a parent process and a child process, both UID 1000. The child does the PR set PDAT sig thing to say I want a certain signal number when the parent terminates. The parent terminates and the child gets a signal. This is what set PDAT sig does. Now, how about this scenario? Starting off the same as before, unprivileged processes, the child sets a certain PDAT signal, and then it execs a setuid root binary, and that setuid root binary ends up changing its credentials to some other user ID. So perhaps all the credentials change to UID 1001. At this point, this process is unsignalable by this parent process because this parent process is owned by a different user. And that means when the parent terminates, the child doesn't get a signal. This is expected behavior. This is fine. Let's go one step further. Same scenario, but now the parent, before it terminates, execs a setuid program that changes its credentials to 1001. Now when that parent terminates, the child gets a signal. Without this PR set PDAT sig option, that parent process would never have been able to send a signal to the child. Okay, so this is interesting for an attacker because now they've got a way of sending a signal to a process that they couldn't signal before. And making programs do strange things is what attackers love. It's the first step on the pathway to some kind of breakage of the system. The thing is, people only realize that 10 years after the system call was implemented. Okay, and they closed the loop or closed the gap there by saying that if a process executes a setuid program or a setgid program or a program that has capabilities, then this attribute, the set PDAT sig attribute, is cleared. Okay, but it took 10 years for people to notice that, and in those 10 years, there was no documented behavior for exec VE and this set PDAT sig feature. So my point is, perhaps if that had been documented and more explicitly thought about at the start, maybe people might have cottoned on to this security problem earlier. Okay, some other surprises. Threads. Now, the original mail message here describes the feature set PDAT sig. The parent process will get a signal sent to it. Sorry, the child process will get a signal sent to it when its parent terminates. Now, if you think process termination means termination of the last thread in a multi-threaded process, then you're in for a surprise. Okay, I think of process termination as being all the threads in the process have terminated. That's the usual definition of process termination. But certainly this was not how things worked, at least not by the time we got the modern Linux threading implementation around about 2003. This is a bug report that someone made in the kernel Bugzilla, and the essence of the bug report is, I have a multi-threaded parent process. It created the child. I expected that child process to get a signal when the last thread in the parent process terminated. Instead, what happens is the child gets a signal when the creating thread terminates. In other words, there's a multi-threaded process. One of those threads called fork. When that thread happens to terminate, then the child gets a signal. Okay? And this person's reasonably saying, that's not what I expected. I expect process termination to mean termination of the last thread. That was in 2012, 15 years after the API was first implemented. It takes a long time sometimes before API misdesigns are reported. Maybe people noticed this earlier, but it never got fed back to kernel developers in any meaningful way until 15 years later. And the sad thing is, we can't fix this. This is Oleg Nestorov in the same bug report saying, yeah, this is ugly, but we can't fix it because there might be other programs out there that depend on the ugliness. At least we can document it, okay? And, you know, okay. The story's actually even a bit worse than this, and I'm going to come back to it. Okay, what about some other pieces here, missing pieces? Back to that original patch message, what if the child process is multi-threaded? When it comes to sending signals to a multi-threaded process, there's two possibilities. The signal might be process-directed. That means the signal will be delivered to an arbitrary thread in the multi-threaded process, or it might be thread-directed. In other words, it's targeted at a specific thread in the multi-threaded process. This is two possible different modes of how signals are dealt with for multi-threaded processes. And of course, the question is, this parent death signal being sent to the child, is it being sent to the process, or is it being sent to a particular thread? Perhaps the thread group leader, for example. Who knows? Because it wasn't documented for a long time. But now at least it is. It's a process-directed signal. And then the child gets a signal, but is that all the child gets? Well, unless you read the kernel source code until quite recently, you wouldn't know. But now the manual page tells us. Oh, and also there's a SIGINFO structure that comes along with the signal that tells us the PID of the terminating parent process. Okay. Oh, by the way, it's the PID of the terminating parent process, not the thread ID of the terminating thread. You want consistency in your API misdesigns? Sorry. Okay. Then there's other missing details. What if the parent terminates before the child does the PR set pdeath thing? Does the child get a signal? Okay, again, the original manual page, the original patch message didn't say, but at least nowadays the manual page tells us. In that case, there is no death signal sent to the child if the parent has already terminated by the time the child does this operation. Which means, by the way, there's an interesting race condition there, because if the parent terminates before the child has a chance to do this thing, then it's hard for the child to detect the termination of its birth parent. Okay. Some more surprises. Again, to do with process termination. Now, maybe the child gets this parent death signal and it just carries on executing. I think the original intent of this feature was, if the parent terminates, the original kernel developer here wanted to have the feature, if the parent process terminates, I want to make sure the child process terminates as well. And that's a reasonable thing to want to do. But there might be people who want to do other things. They want to know, if the parent signal terminates, I'm going to do something. Sorry, if the parent process terminates, I'm going to do something, but then I'm going to carry on. And the question is, well, what if the child does just carry on? So normally, when a child process terminates, I'll rephrase that, once upon a time, normally when a process terminates, it got reparented to the init process, PID1. But that behavior already changed on Linux quite a few years ago, because now we have another prctl operation called setChildSubReaper. And what this allows a certain process to do is to say, if any of my descendants become orphans, in other words, their parent process goes away, reparent them to me, not to the traditional init process, PID1. The most well-known user of this feature is, of course, systemd, because systemd arranges all the processes in the user session to be reparented to a certain reaper process that manages the processes or the orphans in a user session. Okay. Then the question is, well, how does this feature interact with set pdeathsig? Well, because of the sub-reaper mechanism, what this means is just a child process could have a series of parents, because you can have a series of ancestor processes that all set the sub-reaper mechanism. And what will happen is that if the child's original parent goes away, it'll be reparented to the next ancestor sub-reaper. If that ancestor sub-reaper terminates, then the child will be reparented to the next ancestor sub-reaper, and so on. And of course, surprise, surprise, that means the child might get a series of death signals. Okay, each time the child process is reparented to a new sub-reaper. More surprises from threads. And I think it's fair to make the observation that threads caused quite a bit of grief for traditional Unix and Linux APIs. And the point here is that Unix was invented in 1969. Threads got bolted onto Unix systems in the sort of mid-80s. And when those two worlds met, there were sort of API broken pieces after that. And things needed to be fixed. What if one of the sub-reaper processes is multi-threaded? When does the child get the death signal? And you might say, well, maybe it's when the first thread in the parent sub-reaper terminates. Or maybe it's when the last thread terminates. Or maybe it's when the thread group leader terminates. Or maybe it's when each thread in the multi-threaded process terminates. Of course, the answer is none of the above. Okay, I haven't investigated this fully, but this is how it looks things are happening to me when I look at the kernel code that's relevant here, a function called find new reaper. And the way things seem to be implemented is child processes are parented by individual threads in a multi-threaded process. In other words, you might have a multi-threaded process. There are different threads that call fork. That process as a whole has several children, but the children are being recorded as being associated with individual threads in the parent process, which is kind of bizarre, but it's how it is. When one of those threads terminates, what will happen is the kernel then says, I need to find a new thread that can be the parent of this child process. And what it does is search around among the other threads in the multi-thread process, finds a suitable new parent, reparents the child process to that other thread. The child gets a signal along the way. And the order of the search of trying to find a new parent thread in the parent process, as far as I can work out, it's the order of thread creation in the parent. Or possibly it's order of thread ID, I'm not quite sure, but it looks like it's order of thread creation in the parent. So, if the parent's multi-threaded, the child is potentially going to get multiple signals again. And it turns out the behavior is the same for the original parent process as well. If the original parent process was multi-threaded, the same thing can happen. There's going to be possibly multiple signals delivered to the child as the individual threads terminate. How many signals and how many signals are going to get sent depends on the order of creation of threads in the parent process. Question for me at this point is, do I dare document this? Because this is very much a detail of internal implementation of how the kernel is managing the organization of processes in its data structures. So far, I didn't dare document it. I only remarked this behavior about a year ago. And the thing is, though, I haven't documented it so far, but given enough time, users will invent every possible use case for an API. They'll exploit every possible behavior of an API, either deliberately or accidentally, even if you don't document it. So, what happened? What we wanted was the child process should get a signal when the parent terminates. What we got was this. If the parent is multi-threaded, the child gets a signal when the creating thread terminates, not when the process terminates. The child might get multiple signals if the parent is multi-threaded. The number of signals the child gets is going to depend on order of thread creation in the parent. Each one of those signals has the same SIPID value, the same parent process ID. And what we get, of course, here is accidental exposure of how the kernel is implementing its management of processes. And if there were ancestor sub-reapers, then the child's going to get potentially one signal for each ancestor sub-reaper that eventually terminates. And if those sub-reapers are multi-threaded, see above. Oh, and if the child process was trying to work out when did its birth parent terminate, there's a difficult race condition here to solve. And we had a security bug, which took a while to find, but eventually did get fixed. Oh, and we had this API inconsistency between the get operations in the prctl system call. Okay, I think it's fair to say that probably quite a few of these behaviors were unintended. They were rather accidental. And the question is, well, why did this happen? And there's various ideas that I would put forward here, and I want to elaborate on some of these in the remaining minutes. One of them is that there's no one person or group who owns the interface. And there's often insufficient description, documentation of what we're doing. There's not really people who are looking, or not enough people who are looking at the big picture. How do these different features interact with one another? And even as I think this example shows, sometimes there are quiet changes in behavior. The new threading implementation, I think, changed how set PDAT signal operated, for example, when it was added in 2003. And another observation is that sort of the decentralized design model that we've often followed in Linux, it often fails us. So, a little bit more detail on these points. So the question is, who owns the interface? And what I mean by this is, who decides what the contract is that is being provided by the implementation of an API and the consumer of that API? And the answer really isn't simple, and that's part of the cause of the problem. And I was already talking about this 10 years ago. I thought about recently, this is a presentation I did at the first Linux Plumbers Conference back in 2008, that URL down at the bottom. Now, you might say, well, it's obvious. It's the kernel developers who define the interface because they wrote the code that implemented the interface. Obvious. But there's various points that contradict that sort of obvious assumption. What if there's a bug? Some unintended behavior in the interface? You know, what is the contract then? Or maybe users find some unforeseen use of the interface. You know, what is the contract then? And then there's in the between, there's glibc. glibc provides wrappers for a lot of system calls. So glibc provides these wrappers for a lot of system calls. Sometimes those wrappers change the behavior of the underlying system call. What I mean by that is the wrappers do some extra stuff on top of the system call. And you might use that to argue perhaps it's glibc that is defining the contract. But you know, in a lot of cases, the wrapper function in glibc is just trivial. It's just exposing the kernel's behavior unchanged. Sometimes it's an awfully long time before an API gets a wrapper in the C library. I think it was it last year or this year? Certainly very recently, getTID, after 18 years, it was this year, I think, earlier this year, finally got a wrapper function in glibc, 10 years after I made the bug report. And there are various other APIs that aren't conventional system calls. Things like proc files, sys files, ioctl isn't really a system call in the traditional sense. These aren't wrapped by glibc, so glibc is not involved. So this argues against glibc as defining the contract. Is it me? Okay, I maintain the Linux manual pages, the documentation of the behaviors of the interfaces. And the idea here is, let's document exactly what the interface provides in terms of behavior and what users should expect. And that documentation can act as a specification for testing. Perhaps it's me, except I know that many things remain undocumented, and of course sometimes the documents are right and the implementation is wrong. What about the users? Could it be that the users define the contract, which might initially seem to be a nonsense idea? How could it possibly be the API consumers that define what the contract is? Well, the thing is, given enough time, collectively, your users, the API users, will discover every possible detail about the interface. They'll read the source code, they'll look at exported symbols, they'll try stuff. Eventually, they'll discover everything about your interface, and they'll rely on it one way or another. And some of those discoveries are deliberate. Users deliberately, they go investigate and they find a certain feature. Oh, I'm going to use that feature. Sometimes they're accidental. Users write code that happens to depend on an undocumented, unforeseen behavior of an API. They might even write programs that depend on buggy behavior in the API. And some of those behaviors in the API might have been things that the original implementer never even thought of. An ancient example which I like to roll out is file permissions that look like this, where we've got file permissions where you've got user has certain permissions, world has certain permissions, group has none. That means users in a certain group can't access that file. That's the meaning of that mask. It surprises a lot of people. There are applications out there, I've never seen them, but I know they exist because several people have told me, that depend on that oddball feature, that oddball corner of behavior. Okay. What else do we have in terms of causes? This was the original documentation. This was the original documentation of the set pdeth signal interface. This is what it looks like now. Okay, now the gap between these two things, this represents, well, mostly stuff that was implemented but unknown at this time that later became known. Okay, yes, there is some behavior that is new since the original implementation, but a lot of the behavior did already exist in 1997, but it was not explicit. And there's still one piece that I am slightly afraid to document. Now, what are the problems that come from this lack of documentation? Perhaps if the exec VE semantics had been documented up front, people might have realized that security vulnerability earlier. If the kernel's semantics of how child processes are reparented when a parent thread terminates were documented, perhaps we might have, well, first of all, realized this is slightly insane. Child processes should be children of parent processes, not parent threads. And then we might have realized what the implications are here for this PR set pdeth sig feature, where a child might actually get multiple signals because the parent is multi-threaded. Perhaps if the documentation was written as the API was implemented, it might have helped reviewers spot those problems. Documentation essentially lowers the bar for code review. I've been saying this for years, but still, it's... Okay, of course it also provides a specification for testing. Okay, because how can we do tests if we don't have a specification? I won't even try and talk about the plight of the sorry users of the APIs when there is no documentation. They are just sad. Okay, now, coming back then to this idea of interactions across the interface. prctl pdethsig, it's almost a mini case study in what happens when you fail to consider interactions across the interface as a whole. And we see some interesting behaviors here because of threads, because of process termination, because of exec VE, and there are other features that when it comes to APIs I think especially are always worth considering. What about process creation? When a new child process is created, what does it inherit from the parent? What does it share with the parent? Signals. When there's signals in play, are the signals process-directed, thread-directed? What information comes with the signals? If file descriptors are in play, then there's the question, a file descriptor refers to an open file description. And you can have multiple file descriptors in the same process or in different processes that refer to the same open file description. And this is because of things like dupe and fork and so on. And that sort of one or many-to-one relationship has resulted in some really unpleasant corner cases in the behaviors of various APIs, things like signalfd and epoll, and historically on Unix systems, fcontrol locking. And of course these lists are far from complete. Then, decentralized design. I think decentralized design, it often fails us. For example, a simple example here, the inconsistencies between the different getters in prctl. Some of them return the result as a function argument, some of them return the result as the function result. And this confuses users. They make mistakes. The addition of NPTL in the native POSIX threading Linux, native NPTL threading implementation in 2003 almost certainly changed the behavior of oh, that's a typo there. It should say prctl pdethsig. Okay, and the point is, we get this strange behavior with multi-threaded process. The addition of child subrepos in 2012 also changed the behavior, and it magnified this previous point. And I think in each case the issue was a failure to see the bigger picture. How are things interacting? And some of those problems only get noticed much later, and this is a pattern I've seen consistently. So the exec v security issue, that was noticed 10 years later. The bizarre multi-threaded parent process behavior, that was reported only after 15 years, and by this point it couldn't be fixed. And these are not isolated cases. So, for instance, back in Linux 2612, accidentally, the behavior of the fcontrol fsetOwn operation was changed. By the time the change was noticed, and again the change was to do with threaded processes, by the way, by the time that change was noticed about 4 years later, it was too late to fix it, because maybe there were new programs that depended on the changed behavior. So now we have fsetOwn EX, which lets us do what fsetOwn used to do. Sometimes users simply don't even know how to report API issues. So a few years ago I had a POSIX, a bug report against a POSIX message queue API change that was reported to me as, oh, the manual page should be changed. But what had actually happened is that someone had accidentally broken a certain part of the POSIX message queue API, and the user at the end of all of this said, oh, the manual page is wrong. Okay? And they even knew that behavior had changed because their program that formerly had worked now didn't work any longer. And so they sent me a bug report saying, fix the manual page. And I got in contact with the kernel developer concerned and said, fix the kernel. Okay? And that's what was done. But users often don't know how to report the problems, and it takes them a long time. So this feature is a small lesson in the school of we don't do decentralized design well, and we've had much more spectacular lessons. Okay, C Groups version 1, anyone? Or the Capsys admin capability, which is a horrible mess where let's divide the power of superuser into small pieces. Oh, and let's make one of the pieces 40% of the power of superuser. That's sad. So we have too few people who are looking at the big picture. Not enough people with the motivation, time, knowledge to consider things like API consistency and interactions across the interface. And all I want to say is why isn't there a paid kernel user space API maintainer? It surely is time. And once upon a time I would have wanted that job. But I think it would be great if someone else got it now. Okay, so here's how things would look in my ideal world. Okay, we're good for time. And when I say my ideal world, we can't achieve perfection, but we could do things better. Let's try and reduce the problems. We can't get rid of them all, but we can reduce them. So, first of all, every patch that changed the interface would CC a mailing list called Linux API, and every kernel developer, who's a kernel developer in this room? Yeah, would remind everyone else who forgot to do that. Okay? This list was actually set up at my instigation about 10 years ago because it's intended to advertise API changes so that people who are interested in the API can notice the API changes and perhaps respond to them, perhaps critique them, but deal with this information. Because part of the problem that I have, and other people have it as well, is how do we even know when an interface is getting changed? It's not always easy. There's 1,000 messages a day on LKML. No one is reading all of those. And there's plenty of other mailing lists as well. And the people that subscribe to this list include C library developers, strace developers, testing project maintainers, and some people who just care about APIs, and me. Okay, because I'm interested in this information for the Linux manual pages. Every commit message, but especially those that change the interfaces, would tell us a story explaining why the change is being made, including explanations about why certain features are being added, and explanation about why certain features are not included in the API, and URL references to mailing list discussions, and a version history explaining the history of the change of that patch over time. And this is not that difficult. And if you think it is, go and take a lesson from Christian Brauner. He'll show you how it's done. These are a couple of his commit messages that I've been looking at recently, and I'm very thankful for them. Okay. Kernel developers, when they're adding new interfaces to the kernel, should always be working directly with the glibc maintainers. One reason is to make sure that support is added in glibc at or soon after the same time as the feature is added to the kernel. And the glibc maintainers or the glibc developers are really good at spotting API design problems that might make user space programmers unhappy. Every new feature would have tests, of course. There is k-self-test nowadays, so things have got better, but they could get much better still. There's still a lot of stuff that gets added to the kernel in terms of APIs that doesn't really have enough tests in k-self-test. Every feature that's being added to the kernel should have, or API feature, should have a real-world user that provides both a first test of the implementation, but also a first test of the design. And we've repeatedly had the situation where some fairly major API gets added to the kernel without any real user of that interface yet. And I think one of the more spectacular examples in recent years is iNotify. iNotify is a really useful thing, but when you look at it closely, you see that it has many problems, and some of those problems, at least, I think would have been sorted out if there'd been a real user who critiqued the design before the API was actually finally merged into the kernel. And there's an article there that I wrote about all the design problems in iNotify, and there's quite a few of them. A manual pages patch would be written in parallel with development of the new interface. I'm still waiting, Tycho. Not as an afterthought. Okay, and there's two reasons for this. One is, I think when you write documentation for an interface, it's a great trigger for making you think about the design of the interface, you as the developer. But the other is, it lowers the bar for other people to review what you're doing. It lowers the bar for understanding. Okay, and of course end users are going to thank you for that as well, and so will I. And that's actually all I've got to say. Thank you very much for your time. And I think we have a few minutes of questions if there are any.
Thank you very much for your presentation. It's time for questions. The first one.
So thank you for the talk. So you mentioned at the end, like very nice, the outline of things you'd like to happen, like in community and so on. So you mentioned you had a talk at Plumbers, like 2008.
Mm-hmm.
Have you had any more recent discussions, like with maintainers, Linux Foundation, and about like how to make maybe, I don't know about this full plan. It might be, a big change for the current process, but how to start moving towards that direction, like?
I haven't had too many formal discussions. I think, I've sort of mentioned the idea, and I'm not the only one, of having a kernel user space API maintainer over the years. The problem is who's going to pay for it. And it could be the Linux Foundation, but it could be.
It's
but
logical, please.
I haven't tried to explicitly argue that case. For about 10 years ago, for about 6 months, I was paid by the Linux Foundation to work on manual pages, and informally there I was also doing API design review in a much more full-on way than I'd been able to do previously. Maybe I should try and have that conversation to get someone else a job.
Okay, yes, thank you. Next question. Okay,
Thank you for the talk. On the last couple of slides, you said a few words about how to prevent such things in the future. Yeah. Do you know, the question is, do you know any work happening right now in order to prevent, in order to do some housekeeping and like deprecate some features and remove them eventually?
It's generally very difficult to remove features because there's almost always at least some user out there. So sorry? And yes, that's security bugs are one of the rare cases where stuff really does get changed. But in terms of features that may seem obsolete now, it's almost always the case that there's some ancient user space binary out there that depends on the behavior, and we don't break those binaries. So there's nothing gets cleaned up generally.
but maybe some deprecation process like that lasts for several years and then like warns the user that his app will never work.
So the thing is, one of the virtues of Windows, let's say, is you can take a binary that ran on DOS in the 90s and you can run it on a modern Windows system in many cases. And I think that's a behavior that we should aspire to on Linux as well. So, no, we don't remove stuff.
Yeah. Thank you.
Thank you.
Oh, there's another question there, I think.
Yep.
Thank you for your speech. So about ideal world, we know that complexity is killing. All projects fight with it, but as Richard Feldman says, we know only that one thing contains with another things, and maybe is possible to fight with dragon of complexity with increasing information flow?
I would say yes.
But maybe there is no people who read all man page, except you maybe.
No, I didn't read all the manual pages.
But if all developers will subscribe to subscribe to
Linux API.
changes, yes.
Yeah.
And if they will flow in huge amount of information of changes, when they will write code and do something new in ideal world.
Yeah, but see, when it comes to, say, the mailing list, that Linux API mailing list, I'm not really asking developers to do anything else other than, when they make the change, CC that list. That's all. And when it comes to adding new API features, okay, that's not all I'm asking. I'm asking them to write some documentation as well. You know? So, but if we don't do this, and then we end up with this API mess, and it lasts for years for user space. So there is work to be done, but I don't think it's an impossible amount of work for developers. You know, what I'm trying to say is there are some simple steps that could make things much better. Write documentation that goes with your patch. CC a mailing list. You know, those are low-hanging fruit. And nevertheless, there's plenty of new APIs that are added to the Linux kernel where that doesn't happen.
Okay, thank you. One. Yep.
So I think I agree with very simple steps, and I think that's where it should be going. So I think one problem with the approach is when a kernel developer, when you make a change that affects the interface, CC mailing list, is that many of these changes that you mentioned during the talk, they're not going to be so straightforward. So you might affect some API in a way you don't know. Yes. And then we either end up with everyone CCing every single patch, and then the whole thing is like, the API becomes, we have the second Linux kernel mailing list where things are just way too much, or when we only get explicit changes. But I think for even explicit changes, it might be first good step.
But so that's where another thing that I mentioned there comes into play, I think, which is let's have a person whose job this is, because look, we had the mess up of cgroups version 1. What did we decide for cgroups version 2? We'll have a maintainer. There needs to be someone who's looking at this. There's some other, there's some things that individuals can do, but there needs to be someone who's trying to focus on the big picture. And it won't be perfect, but it can be better.
Okay. Thank you. The next question, please.
Are you aware of any automated systems to test such APIs? And do you think it's possible, or maybe you are aware of systems that would somehow apply maybe artificial intelligence to discover interplay between various parts of the API? I'm not aware of it.
Thank you, thank you. I'm not aware of any AI project out there that is trying to do this. There are fuzzing projects that try and test new interfaces, but I think the point was well made here that you need a specification in order to understand and test a new interface, or understand its critique its misdesigns.
Okay.
Thank you for the talk. It's very interesting. You made a point that there was almost certainly a behavior change in 2012 when they put in the new kernel threading implementation.
And that was 2003.
Yeah. Okay. Whenever it was. And you also made this point about there's some behavior that you're afraid to document. And I wonder if there was this behavior change and nobody noticed exactly, does it matter?
Well, like I noticed, and okay, it's not hurting me because I was just doing some discovery. But look what happened 15 years later. 2012, someone reported a certain buggy behavior to do with multi-threaded parents, and they said, "This is biting me." Now, the other piece of behavior that I'm talking about here, where there might be a series of signals, no one's complained about that yet. First of all, that doesn't mean no one has been bitten by it yet. They just didn't know how to report it. Or maybe they are yet to be bitten by it.
But if even you are afraid to document some behaviors, doesn't that mean that
Well, I'm afraid to document it because it is really, what's being exposed here is implementation details of how the kernel is managing processes. And these details should never have been exposed to user space. And the question for me is, should the kernel be fixed or should I document this? And I don't know what the answer is.
Okay, thank you.
Okay. Thank you. I think we have time for the last question.
So, from my perspective, the way I used to write the kernel code is usually that when I have some problem to be solved, I try to look for other examples of solving a similar problem. So from my point of view, after a couple of years, kernel is repeating constantly the same patterns in many different subsystems and drivers. It has a positive way that you open different piece of kernel code and you know what's happening because you already seen that pattern. But the thing that I believe is a little bit missing is the documentations of the patterns that we are currently using.
Mm-hmm.
And this way, for example, like we had the GPIO, the old GPIO SysFS API, and it has been recently changed because we already discussed that it was bad, it has certain issues. And the thing is that the same pattern is repeated in different places in the Linux kernel. And what's even worse, even if we already discussed that it is bad for this particular subsystem, and in general this pattern is bad, we see new drivers and new subsystems following the same path and introducing the same type of the API. So do you have any idea how we could solve that issue and how we could, maybe creating some kind of kernel patterns, documentations, or guideline for designing the API?
So I think what you're really saying there is the same problems exist for in-kernel consumers of kernel code.
So there is a certain pattern, for example, how the SysFS GPIO API has been designed, right? You have the export file, you need to write something, a new directory will appear, and then you can do something. And yesterday we had the talk, for example, about the MDEF, and basically I see pretty much the same pattern. You have a file to which you have to write something, new directory will appear, etc., and then you do something. And I expect that this subsystem or driver has been introduced later than we started the discussion about changing the API in GPIO. So the question is how to avoid that kind of situation, that in one place we are discussing that this design is wrong, and in the other place we are already introducing the same design because it is in the kernel.
I think the problems are largely similar and the solutions potentially are largely similar as well. More documentation, more review. It's, the thing is everyone wants to write code, and less people want to review, and even fewer want to document. And this causes these problems.
So the main point that I'm trying to make is that I have never seen a documentation of kernel design patterns. I have seen a lot of documentation about interfaces, about particular subsystems, etc. But there is no a general documentation like this is the way how we currently design interfaces.
Because no one wants to pay for it.
Yes.
No one wants to pay for it. But it hurts. It hurts in the end. You know it hurts. But no individual manager at an individual company wants to pay for this.
It is a problem. Right?
No.
Okay, now it's time for you to pick up the best questions from what you get while that time.
I liked your question, the first question, the most, because I think maybe it'll actually make me do something.
Okay, thank you very much, and this came to Yelena. Thank you.